let me start the last lecture of our course Hodge theory. Okay, so the topic of this lectures is about Hodge cycles, about algebraic cycles. Okay, so let me see. Matheus, tá vendo, não?
Tô sim, professor, tô sim.
So, okay, let's redo the things.
Mas você ainda não tá compartilhando tela, né?
Okay. Okay. I have to. Present your entire screen. Ok. Agora tá vendo o file PDF, não?
Sim, agora eu tô.
So the topic of today is about algebraic cycles. And even so, algebraic geometry is well developed, and we have a lot of data, propositions, theorems, and so on. But our understanding of algebraic cycle is very poor. So I will start the today's course with this quotation from Pierre Deligne, one of the founders of modern algebraic geometry. And at the end, you see that he confesses that there is no method to construct algebraic cycles, and the construction of algebraic cycles was important in Grothendieck's program for the wave conjectures. And even so, Deligne proved the wave conjectures, avoiding this philosophy of Grothendieck in order to construct more and more algebraic cycles. And that's one of the reasons why Grothendieck was not happy with Deligne's final solution to wave conjectures. So constructing algebraic cycles has to do with motives and so on. So, but anyway, just to mention that we don't know too much about methods. We don't have any methods to construct algebraic cycles. So let me go again to Fermat variety. So the hypersurfaces. So let's start from hypersurfaces of even dimension. Even dimension because the cohomology of a hypersurface is mainly non-trivial in the middle one. And in the middle one, if we want to have homology classes supported by algebraic cycles, we have to assume that the middle dimension is even. And okay, so one trivial algebraic cycle is to take a linear cycle of dimension n½ plus 1, n being the dimension of the variety, and to intersect it with x. Here in this context, I have taken the coordinates x0, x2, xn minus 4, xn minus 2. This will give you this linear cycle. And when you intersect it, you will get an n-dimension, let's say, n½ dimensional algebraic cycle, and it will induce homology class in Hn. And this is also called polarization. Usually, when you take it to cohomology, it's called polarization. And and it turns out that they are all homologous to each other, because this p_n½ it can move smoothly to any p_n½ plus 1, and so they are all homologous to each other. So at the end we will have just one homological cycle, and we can verify that its self-intersection is D. Maybe this self-intersection is just, let's say we can, in the topological context, is just a homological class of Z infinity intersected with the homological class of Z infinity. So the point is that we have this intersection map from Hnx times Hnx to, let's say, if the homologies are defined over C, to Z. Okay, so this is the one algebraic cycle that that we have, and so we concentrated on Fermat variety. So you see that the Fermat variety has a lot of automorphism. For example, since maybe later x0 to the d plus x1 to the d plus blah 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 plus xn plus 1 to the d equal to 0. And you see that if we permute the variables, the Fermat variety is invariant, and even we can multiply the variable by roots of unity. So it is still invariant. So there is this okay, it is automorphism group is huge, and so this one I will use as in order to if one we construct one algebraic cycle, then we apply this this automorphism group and to get more algebraic cycles at the end. So this means about, well, the permutation group together with the multiplication of coordinates but roots of unity, yeah, they will give us this automorphism group. Anyway, let's go on to see in the case of what kind of algebraic cycles we have in the case of Fermat variety. So and the Fermat variety has a special linear cycles. This projecting spaces of dimension and half, and for example zeta 2 here is the root of unity. So x0 minus zeta 2 x1 equal to 0, x2 minus zeta 2 x3 equals 0, and so on. And this is the reason is that when you write x0d plus x1d, so just write this one together, and then x2d plus x3d, and so on. So write the Fermat variety with variable x0 and x1 together, and then you write the decomposition of this x0d to the plus x1d. So this there will be this factor, and in the same way this will appear in the factorization of this one. At the end you will see that this guy is some subvariety of the Fermat variety, and since everything here is linear, so all these things are linear polynomials. At the end, this is just a projective space of dimension n half, and so we get these algebraic cycles. And of course, and as I said, since this guy, the Fermat variety has a lot of automorphism, at the end we can introduce all linear cycles inside in the Fermat variety. So by just this P here is the permutation of the 0, 1, 2, n plus 1. And A is just, let's say, this root of unity. Anyway, and well, this one, let me just not to concentrate, but we have a lot of these algebraic cycles. But maybe if we count this number of linear algebraic cycles, it will be just this number. So this is a kind of elementary problem. So this GDN was the group of automorphism, which was basically permutation and multiplication by roots of unity. And then we have to care about which elements they fix one algebraic cycles, and when we count, we get this one. Maybe I have to remember that in the case of n equal to 2, and n equal to 2 and d equal to t, this is cubic Fermat surface. This number is 27. So I don't know. And this is the famous 27 of lines, 27 lines in a cubic surface. So the theorem is that in a cubic surface in P3, it had 27 lines. And in the case of Fermat variety, we can explicitly write down this 27 lines. Okay, so you see that at the end of the day, for Fermat, we can construct these algebraic cycles. But of course, if it is arbitrary surface, we don't have any method to construct algebraic cycles. Okay, and okay, maybe maybe one nice observation is that with this condition, degree being bigger than n½ plus 1 and the n bigger than or equal to 2, then any linear projective space. So if at some point you have P_n½ inside the Fermat, let me see. Oops. Okay. Inside the Fermat of degree t and dimension n. Just a moment. Oops, what's happening? Okay. Then, so it can happen that we have a projective space of dimension n½ inside the Fermat, and it turns out in this case all these linear cycles are the ones that we obtain from the one that I wrote, and then it's and the action of the automorphism group of Fermat on the one that I showed. Okay, so this is let's go forward. So let me. Okay, maybe before let's. So the point is that in a moment I will show that these linear cycles are enough to verify the Hodge conjecture just for very special degrees, not all degrees. But anyway, the issue of trying to construct more algebraic cycles of dimension n½ is open. The next class actually has to do with our Kishida algebraic cycles. And again, this is a kind of elementary high school mathematics that you play with the equation of the Fermat, and you try to find more algebraic cycles. Maybe just in this case, okay. Anyway, this is this one. Let me just don't focus on this the Fermat. But anyway, again, you start playing with the equation of the Fermat, and you try to write down in terms of this symmetric functions, and you get new algebraic cycles. But okay, I will not focus on this one for the moment. Just let's take these linear algebraic cycles as our main examples of algebraic cycles. Okay, so maybe I will start writing. Stop sharing. Okay. Now back to back to the draft. Okay. Okay. Let's assume that you have a variety X, and you have projective variety. And you know Hn, but you have computed the Hodge cycles of this guy. In the modern languages, let's say X, this, let's call this H and half of X intersected with H and XQ. I will end. So you know the dimension of this guy, and this is, let's say, B. And you want to prove the Hodge conjecture for in this case. So one typical way is that to construct algebraic cycles Z1, Z2, Zn, Zb. So you construct B algebraic cycles, let's say, of inside X, dimension Zi being n half, and for simplicity, let's remain in the case of iservative. N is the dimension of X. So once I explained that if Zi's are key linear independent in Hn X Q, then the Hodge conjecture is verified. And the reason was that Hn(x), let's say that H Hodge n x, we have a Hodge n x q, and then there we have this q z1 plus q z2 plus blah blah blah. This is of dimension B, and we know that the q linear combination of these guys are in here, and so this is of dimension B here also. So at the end, it implies that here we must have equality. So this is one way to verify the Hodge conjecture. But we need to know these Zi's are key linear independent. And in order to verify this one, easy way to do this one is to say that to use this simple proposition. If let's form the P times P matrix. What is this P times P matrix? Its entries are just the intersection, the topological intersection between Zi and Zg. So remember that I am using Zi, Zg, this dot, just this is the topological intersection. So the homology class of Zi dot Z Zg. So if determinant of this guy is non-zero, it is easy to see that this is then we have when we have we have Zi's are independent linearly independent in H and X Q. And this is easy to verify. How? For example, if there is a linear dependence, Zi or I equal to 0, I equal 1 to B, and this Ri equal in Q. If there is a linear dependence, so I'm in the proof, then you just make intersection with Zj. This means that this will imply that Ri, Zi, Z. No, so let's take intersection with letter J. Zj I equal to 1 until B is equal to 0. But this will imply what? This will imply that the Za, so the Zj matrix times this vector R1, R2, Rb is equal to 0, and this will imply that determinant of this guy, determinant is equal to 0. And so one way to prove that the algebraic cycles, their homology class is linear independent, is to verify that the determinant is 0, and the vice versa is not true. And actually, the vice versa is true for, let me say, for primitive algebraic cycles, maybe. So if you want to have a, oops, just a moment. What I'm saying that if these Zi's are linearly independent, it doesn't imply that the determinant is non-zero. But if Zi's are primitive, well, whatever it is, then this is the case. Maybe I just make the reference to theorem what was 8384. 83 and 84 in my book. But anyway, for our purpose, this is already enough. If determinant of this intersection is non-zero, then these are Zi's are linearly independent. Okay, so so for the Fermat, we have computed the space of Hodge cycles, and we get a lot of algebraic cycles. P, let's say, I in the index in this way, P and half, I equal to 1, 2, 3, and then it was n plus 1, n minus 1, blah, 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 3, 1, and then d to the n half plus 1. So we had really a lot of algebra linear cycles, and we wanted to know, we want to verify the Hodge conjecture in this case. And so what this means that we have to compute the intersection of these linear cycles. So maybe let us take two such linear cycles. Let's say P and half 1, P and half 2. And well, set theoretically, I have so remember that these are projectives, linear projectives in Pn plus 1. So set theoretically Pn half 1 and Pn half, actually maybe let's follow the notation in my book, not 1 and 2, but Pn half and Pn half check. Okay, so set theoretically they will intersect in some Pm. Because this is given with a bunch of linear equations, and this is given also by another bunch of linear equations, they might have intersections, this linear equation of this one, and that's why we will get another projective space here. And when they do not intersect each other, let's say when this means that P minus 1 will be the impetus set. So set theoretically they can intersect in something, again, some algebraic variety. But the point is that at the end of the day, this Pn half and Pn half check, they induce elements in NHN X, let's say a Fermat. From now, let's say X for me is XDN Fermat Q. And at the end of the day, well, actually, one more stronger, let's say Z. And at the end of the day, there is this intersection. We have to compute this intersection. This is some number in Z. And from the topological intersection, it is not clear what this number is. So the next step in our understanding of the Hodge conjecture for Fermat variety is to compute this this intersection number. Let me share the. Okay. Matheus, está vendo, não?
Tô sim, professor, tô sim.
Okay, so actually, in order to compute this intersection number, there is a well-known machinery in algebraic geometry. It is called the Adjunction Formula. Again, I will not really go into details of this, because this is also, one needs few classes to explain this adjunction formula, normal bundle, Chern classes, blah, 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 blah. But let me just a name in your mind. But using this adjunction formula, maybe I will just show you the results in our context. So the idea was exact. Let me. So for example, here I have taken one linear cycle, the another one. These are not inside Fermat, but no, actually, well, I can put it inside so another hypersurface, not necessarily Fermat. But anyway, let me just show the results. Okay, so in my handwritten, I put it as Pn half check and Pn half. So the result is, assume that the theoretical intersection of these two linear cycles inside a smooth surface, for example, in my case it was Fermat, is a projective space PA. In my handwritten, I wrote it as PM. Okay, but doesn't matter. So if the theoretical intersection is PA, then the topological intersection between these two linear cycles inside the hypersurface has this formula. So this is 1 minus d plus 1 to the a plus 1 divided by d. And this is, note that this is not a rational number. This is actually an integer, because d d here divides whatever is there. And well, I didn't talk about this primitive version of our algebraic cycles. But anyway, what I wanted to say that we can compute the intersection of these algebraic cycles. So let's go to the first result. So maybe I first I introduce this results to Ran Shioda and Aoki Shioda. Suppose that the degree of the Fermat variety is prime number, or d equals to 4, or d is relatively prime to n+1 factorial. Then, in this case, the Hodge conjecture is true, and actually the Hodge, the space of Hodge cycles of the Fermat variety is generated by the homology class of linear half, and in particular, the Hodge conjecture is true. So, well, Shioda and others they proved this one again by computing the dimension, but something which maybe I will back to the. Okay, let's go back to the text once again. And actually, the result that you saw by Shioda Ran, it's our rational numbers. But let me see. Maybe I emphasize here. Okay. So first of all, so far we computed. I always took rational numbers, but actually one can do everything over integers with a little bit more effort. But anyway, let's submodule generated by Pn Hossein by all these linear cycles, let's say. So the method that I introduced at the end, it's basically the spirit of the method used by Shioda also, that at the end you compute the dimension here, you compute the dimension here, and then when they are equal, then this inclusion must be equality. But you can also try to do the same things in what integer. If you have this one here, then you would say that integral, if you have equality, the integral Hodge conjecture is true. Anyway, the integral Hodge conjecture is the Hodge conjecture over integers, and it is since the beginning of the story of Hodge conjecture, it is well known that the integral Hodge conjecture is not true. But anyway, in our special cases that you can try to ask again whether it is true or not. And it turns out that for many examples of D and N, equality happens, and so the integral Hodge conjecture is as I think I have. Let me see, what can I do? Okay, and the machinery that so far I discussed and but didn't give too much details of proof. It is enough to verify this kind of equality by computer. So maybe for this, our integers, what we have to do. The point that here we can choose a basis, delta 1, delta 2, delta mu, let's say delta b. Here we choose a basis of the z module, and here we also choose a basis of this cycles. Let's say p1, p2, pn. And if you compute this determinant, pi, pj, determinant, delta I, delta j. So the point is that topologically we can construct the basis of Hodge cycles. We can compute their intersection. We can compute the determinant of the intersection matrix in the same way in the algebraic side. Let's say they're forming a basis. And at the end of the day, the equality of that these are that's this well this in this inclusion is equality, or let's say this sublattice of the lattice of Hodge cycles is the whole lattice. It turns out to be just this kind of equality of the determinant of the lattices. And all these machinery of all these is already we have discussed. But the point is that you cannot do it by hand, and at the end the proofs goes through computer calculations of these things and so on. And for this, let me share again the screen. Okay. Okay, so so this kind of integral Hodge conjecture for Fermat variety is done in this let me say where. This article by Algebraic and Villaflor. So I mean, just following the same strategy of computing the intersection form of both lattice. Anyway, this is one way of trying to understand the Hodge conjecture. But another way is of trying to understand the Hodge conjecture is trying by deformation, and that's one of the reasons I introduced this Hodge loci and so on. So let's go a little bit. Let me talk a little bit about this one also. So let's stop presenting here. Okay. In the previous lectures, I talked about computing these numbers omega Hn the Rham x delta Hn x. That's our Q Hodge cycle. So I showed how they appear in the formulation of the tangent space of the Hodge locus and so on. And but the point is that the deltas that I had, they were Hodge cycles, and at that time I was not interested in verifying the Hodge conjecture for such Hodge cycles. But let's assume that the now as the delta is algebraic, and at the end of the day you can ask this. So the integration over delta, I will this will be as the same for me as integration of omega over z. And it turns out that whenever you know the origin of your Hodge cycle, you may ask also for computing these numbers, and in a moment I will try to explain for what they are useful. Okay, so in particular, today I want to introduce the formula in Villaflor's thesis. So let's take the hypersurface X given by f equal to 0, and let's assume that X f is of this format. So f is actually x0, x1, xn plus 1. This is the homogeneous of degree d. So at the end is I have the projectivization of this guy, and this is inside en plus 1. And let's assume that f is of this format: f1 g1, f2 g2 plus f1 half plus 1 gn half plus 1. These are again homogeneous polynomials of degree d1, and this is the homogeneous polynomial of degree d minus d1, homogeneous polynomial of degree d2, homogeneous polynomial of d minus d2, and so on. And why I assume that this my f is of this format, because I am interested to this algebraic cycle. f1 equal f2, fn half equals 0 inside x. So if f is of this format, you will see that f1 equals 0, f2 equals 0, fn half plus 1 equals 0. It is inside x. And our linear cycles are of this format. Remember that if for Fermat, x0d plus x1d, blah, 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 xn plus 1, xnd, xn plus 1d. This is just x0 minus zeta 2d x1. And then you put the rest of the factorization of this guy there, here, plus, and so on. Xn minus zeta 2d, xn plus 1, gn plus 1. And so our this is the linear cycles are in this category. So something very important, you see that this z is complete intersection. I mean, I can if I'm interested in this smooth case, even I can assume that it is smooth. But anyway, z is complete intersection inside x, but z itself is not a complete intersection of x with something with some subvariety of Pn plus 1. Anyway, these are a kind of natural cycles that we can produce, and at the end, let me say this x beta. Okay, so I make the propaganda of the importance of this cycle. So this elements given by maybe I have to put the residue here, actually, residue of our z. So these gives elements of the Rham homology, and we can start computing their integration over Z. And one of the things that Villaflor did in his thesis, computing explicitly these integrals. Maybe I just introduce his results. Okay. So the result is very beautiful, and okay, maybe okay. So that, as I said, we are interested to compute this integral, and the P, let's the homogeneous polynomial of this degree, and this ensures us that this differential form here. Let me. This ensures that this differential forms gives us differential form in the projective space, because we have written everything in the homogeneous coordinates. But anyway, let me explain this integral formula. So this there is a 2 pi I here. There is n half factorial here. There is this now integer d minus 1 to the n plus 2 here. So the basic part of the integration is this constant c. This constant c that you see here, and so this c is the unique number such that this happens. And in a minute, I am going to explain what this means. So let me explain what is this c number in the paper. Okay. Okay, so let's see. So when you have the homogeneous polynomial, something that out of this you can construct this Jacobian ideal. X1, xn plus 1. This is the Jacobian ideal inside the Cx. And something there, the Jacobian, this is the Jacobian ideal. And then the Jacobian ring. What is this? This is just Cx. So let's call it the Jacob of F. Jacob of F. So anyway, it turns out that this is a weighted ring. So you can talk about weighted pieces. Let's call it this, let's say S. Dimension, F is smooth. Actually, this is a ring, which is also a finite dimensional vector space. This is a kind of not difficult fact to see. But anyway, we will not need this one. But something that it will turn out that the dimension of the homogeneous piece, maybe the homogeneous piece d minus 1 n plus 2. So what this means that the homogeneous piece of S of this degree, this is of dimension 1. And let's so maybe first so the part that I want to explain, the determinant Jack H congruent actually equal, let's say equal C det Hesse F. Okay. So the point is that okay, the Jacobian of so H is this this map F1, F2, F and half plus 1, and then G1 until G and half plus 1. So this is this map. It is a map from Cn plus 2, Cn plus 2. So if you make a derivation of this one, you will get n half n plus 1. This n plus 2 times n plus 2 matrix, then you will get a determinant. And this determinant, if you multiply with p, it turns out that the degree of this guy at the end is d minus 1 n plus 2. And in the same way, if you take you have f, you take what is the Hessian? This is f, the matrix xi xj. And if you make the determinant of this guy, also you will get the degree of this one. Is this one. So you will get two polynomials, homogeneous polynomials of this degree. In the Jacobian ring, this space is one-dimensional, so this one must be a multiple of the other one. So that's why there must be a constant C, such that this is the multiple of the other one, and this is the constant which appears in Villaflor's formula. Anyway, maybe just more 5 minutes. This kind of results, what you can use it in something called Grothendieck's variational Hodge conjecture. Maybe in 5 minutes I explain just the philosophy behind this conjecture, and then I finish. So the point is something like this. You have X, let's say, for example, our Fermat variety or whatever, and then you have algebraic cycle Z. And just imagine that this X and Z0, actually, they are part of the family. So we have this parameter space, you have point 0, the fiber over 0 is x0, and we have z0. But we have the family xt, but not necessarily z0 deforms in this family. What we did, so what we did, we started to introduce the notion of Hodge locus, let's say. So let's put delta equal to z0. So this is a Hodge cycle, so we can talk about its Hodge locus. So this v delta 0 just parameterized contains T such that the topological class of Z0 continues as Hodge cycle. But what you can also do, you can also talk about this VZ. VZ, it's not, let's say, this VZ T in, let's say, just let's local it T0, such that this X0, Z0 deforms. This is a kind of ambiguous because one has to write down the definition. But anyway, let's go a little bit intuitional. XT and ZT. So anyway, from one point of view, I can talk about the formation of X0 such that the Hodge cycle delta 0 remains Hodge cycles. And remember that Hodge cycle is just a topological cycles. We don't care about algebraic cycles and so on. And from another side, we can talk about a space of parameters T such that ZT also deforms. So, well, it is easy to see that VZ, if you do the proper definition of deforms, is that VZ is Z0, because whenever you deform Z, algebraically, the hope is that its topological class is just the monodromy of the original topological class of Z0. So at the end, this means that when I deform into ZT and I write it delta T as ZT, then this delta D is just the monodromy of delta 0. This can be made exact. And but you can ask when these two question, when equality happens, this means that the only deformations of the deformation of Z0 as a Hodge cycle and as an algebraic cycles are the same. And it turns out that this kind of integral formula that I showed you before, they are extremely useful for this to prove this kind of statement. Maybe I will write few examples of this situation. For example, examples of these situations that one can verify XDN. If you take Pn half, for example, one examples are just linear cycles, actually linear cycles inside any surface, any hypersurface. Another one, for example, if you take two linear cycles, P1 half, Pn half inside X, and Pn half, it doesn't intersect. What this means? This means that we have two linear cycles with no intersection point. Let's say let's take this one. Actually, for this one, I have to take the Fermat. And when you take inside the Fermat, so the sum of these, and then you take the Z, the sum of these guys. Then this means that this algebraic cycle, the only way to deform this algebraic cycle, let me say in this way. The only way to deform this Hodge cycle, topological class of this, Hn, the only way to deform this Hodge cycle is to deform it algebraically as a separate union of two linear cycles. And okay, as I said, this is kind of the beginning of another story. And so I finish it here.